Welcome all. I wanted to make this video in English so that I can add it to my portfolio. Okay, in today's class we'll be learning about the force acting on a current carrying conductor placed on a magnetic field. The basic principle is this: when a current carrying conductor, say a copper wire, connected to a positive and negative terminal of a battery, when placed inside a magnetic
We got a
field,
small experimental setup
experiences
here
a force.
in which
What do
you
you
can
say?
see the bar
Can you try
magnets
this?
north and south. Also you can see the current carrying conductor connected to the positive and negative terminal of a battery. But never connect like this. Do not connect the positive and negative terminal, because due to no resistance this will damage the equipment and causes fire. I am going to use only 2 volts here. Also we have a weighing balance, and you can see the current carrying conductor, it flows between the magnets, between the uniform field of the magnet. And now I am going to give a supply of 2 volts here. Observe what's happening to the weighing balance. You can see the reading of 0.03 grams.
We all know that the weight of an object is nothing but the force of gravity acting on that object, right? And according to Newton's second law, force equals mass into acceleration. And in the case of our experiment, the force acting on the wire or the current carrying conductor equals to the mass, the reading that we got from the weighing scale, multiplied by the acceleration due to gravity, which is 9.81. When we do the math, the value of force is around 2.943 into 10 to the power minus 4 Newton. The value of force may be very small, but remember, there is still a force acting on the current carrying conductor. But the question is, where does this force come from? Interesting. You want to know it? Yes. Around 19th century, at 1820, a Danish physicist called Christian Ørsted, he discovered that the current carrying conductor generates a magnetic field around it, which is a very important discovery. Okay, whenever a conductor carries current, it generates or produces a magnetic field around it. I have talked about this in a video called Faraday Law in our channel. Please see that video for better understanding, because you people should definitely know the direction of the magnetic field around a current carrying conductor to understand
We have a circuit
why
here,
there is a force
batteries, we have
acting on the
resistors,
conductor here.
and also we have
what's the
compass,
simulator?
which is a magnetic material here. Now watch carefully and observe what happens when I close the switch or when I complete the circuit. The magnetic needle deflects. The magnetic needle is a magnetic material, so which can be influenced only by another magnetic field. Am I right? If that's the case, then there must be a magnetic force happening around when I close the circuit. So I can conclude that the current carrying conductor produces a magnetic field around it. But how can we visualize this? Here is an example. So when the current is upward, then this is the direction of your magnetic field generated around the current carrying conductor. To remember this, you can use your right hand. If your thumb represents the direction of the current, then the way your fingers fold, the other fingers fold, represent the direction of the magnetic field around the conductor. Now if I increase the current, you can observe that the magnetic field strength around the conductor is also increasing. Also, if I change the direction of the current, the direction of the magnetic field also changes. So these are some of the observations we can see by use of the simulator.
Now coming back to our experiment, we had two magnets both facing the other pole, and I arranged them as close as possible because I can get a uniform magnetic field between them. Look here, you have to have this in mind. the magnetic field is always directed from the north pole of a magnet to the south pole. Please watch the video on magnetic field in our channel for better understanding. Yeah. And also, we placed a current carrying conductor in this uniform magnetic field. And this current carrying conductor is connected to the positive and negative terminal of a battery. The current in the current carrying conductor flows in this way, conventionally. But we know that electrons always travel in the opposite direction from the negative terminal to the positive terminal. Okay. Now, when the current goes this way or when the current flows in this direction, they generate a magnetic field around a coil like this. See, the magnetic field, the field lines come out of the board and again it goes inside the board. Okay. This magnetic field line indicates that what happens if I place a north pole here. If I take this magnet that have the north pole and if I place it here, I will show that with the magnet. Okay, I have a magnet with me and this is my north pole. If I place my north pole here, the arrow denotes that this north pole will be pushed out of the board. Okay. Now if I place the south pole here, the field line that comes this way, it attracts a south pole. The field line shows what happens to a north pole. Okay, the north pole will be pushed. So if the north pole is pushed, then the south pole must be attracted. Yes, so the south pole comes out of the board again. So both these poles, they come out due to the magnetic field generated around the coil. This magnetic field generated around the coil is pushing the magnets outside. Now according to the Newton's third law, these magnets exert an equal and opposite force on the wire, causing the wire to go inside. Okay, and this is how the force is delivered on a current carrying conductor, or this is how the magnetic force is given on a current carrying conductor. Got it? Now, imagine if you don't have a weighing machine. Is there a formula to calculate this magnetic force on a current carrying conductor? Yes, there is. So, by repeating the experiment and by observing the experiment carefully, we can notice certain important things. For example, the force acting on the wire is proportional to the length of the conductor. The length in the sense, the length of the wire that is under the influence of the magnetic field. Okay, this part. And also the force acting on the wire is proportional to the current on the conductor. More the current, more the force will be. Okay. Now, the force, it also depends on the magnetic field. Magnetic field is nothing but the area around the magnet in which the magnet can exert force on something. Right? Here comes the term called strength. Strength is nothing but force over something. So if I can deliver a large force on an object, then I can say that I have a good strength. My strength is high. Similarly, the strength of this magnetic field, okay, the strength of the magnetic field is nothing but the force on the conductor. Right? Do you get it? The strength of the magnetic field here, okay, is nothing but the force delivered on the conductor. That denotes the strength, or that says how strong the magnetic field is around the magnet. Okay, and we cannot just write force over conductor, correct? Because that force, it depends on how long the conductor is and how much current is available in the conductor, or how much current flows through the conductor. Hence, force over the conductor with a specified length and a specified current flowing through it. So this is what we use to calculate the force. If I rearrange this, I get force equals magnetic field, or the strength of the magnetic field multiplied by the length of the conductor, and the current flowing through the conductor. Okay, and this is true in the case where the current and the magnetic field are perpendicular to each other. On the other hand, if there is an angle involved between the current carrying conductor and the magnetic field, then we have this formula: force equals magnetic field, current on the current carrying conductor, and the length of the conductor multiplied by the sine theta. Theta denotes the angle between the current and the magnetic field. So this is how the force is produced around the current carrying conductor placed in a magnetic field. Okay, and also there is a different method to derive this force. This force is called as Lorentz force. Okay, this force is called as Lorentz force. It also can be derived using another method which involves cross product of vectors. Also, the force on a current carrying conductor can be related with the drift velocity of electrons. But these two topics are for another video. So I hope you understood the concept of magnetic force on a current carrying conductor. And yes, see you on the next video. Thank you.